Welcome to episode 3 of Retro Programming on the Commodore 64. In this episode I want to talk about sprites and character graphics, and we should have a look at raster lines and how to time your code. But before going any further, I just want to quickly mention there's been an update to the CBM PETSCII Studio. However, it seems to have given a lot of trouble to people, including myself. When you want to run your code, it doesn't load and run it correctly. So as a workaround, I've added a link where you can download the previous version. That seems to work fine for everyone. So there's a link in the description. If you have any trouble with the latest version, just download the previous version and that should solve the problems. Okay, let's get started. So while we do have both Sprite Editor, Character Editor and Screen Editor built into the CBM PETSCII Studio, I would like to introduce another tool I found very useful. This is called the PETSCII Editor, and it runs in your browser. You can see the URL here. I'll leave a link in the description. So I think this tool is very useful when you want to play around, maybe you want to mock up some screens, create some characters, create some sprites and see how it looks together. So let's try it out here. I'll just resize this a bit. And let's start looking at some sprites. Let's say edit sprite set here. And it starts out with the balloon sprite from the Commodore 64 user manual. Anyway, we're not going to use that. I'll just create a new one. And I'll just set the background to black. It's kind of nicer to work with. So for single color sprites, the size is 24 pixels across and 21 pixels down. So that might seem like a little bit strange size for a sprite. Why is it not 32 times 32 or 24 times 24? Well, on the Commodore 64 they have allocated 64 bytes for each sprite. So 3 bytes across and 21 bytes down. That's 63 bytes, and then we'll have 1 extra byte between each sprite. So that's the reason for the size. And we can have a maximum of 8 sprites on screen at the same time. Of course, we can do some trickery to expand that number, but if we want to do things like my small introduction to this episode, where I have 32 sprites moving all over the screen, then it does get very tricky and it's difficult to do other things at the same time. Anyway, with single color sprites, you can use any of the colors up here for your sprite, but you're limited to 1 color per sprite. But we do have another option, that is the multicolor sprites, and it's probably the most used on the Commodore 64. This gives you an option of having up to 3 colors per sprite. However, you have to be aware that 2 of the colors have to be shared among all your sprites, and then you have 1 individual color for each sprite. And of course, since we still only have 64 bytes for each sprite, and we now need 2 bits for each pixel for the extra colors, that means we only have half the resolution across now. So before it was 24 times 21, now it's only 12 pixels across and 21 down, but the pixels across are kind of elongated, 2 pixels put together. So you can see it if I try to draw something here. The pixels look very different. So that's one of the challenges of making sprite graphics for the Commodore 64. Anyway, let me try to draw a sprite here we can play around with. So as I'm sure you can tell, I'm no graphics artist, but it kind of resembles a Pacman monster. And to illustrate the reuse of these two colors here, we can try and make a copy of this one, add a new one, paste it in here, and then we can change the color so we can have monsters in multiple colors. So let's have a look at some character graphics. I'm just gonna click on screens over here, and we just say edit on this screen, and what we get here is kind of a representation of the Commodore 64 screen. I'll just enable a grid here, and we can pick characters over here and we can start drawing stuff. So one thing worth noticing is the size of the Commodore 64 screen, the whole resolution. So it's 320 times 200, so 320 across, 200 down. However, if we use multicolor, then it's only 160 times 200, because it's the same thing as with the sprites, where we need 2 bits per pixel instead of 1 bit per pixel in the high resolution mode. And for characters here, well, we can see 10, 20, 30, 40 times 25 down here. So 40 times 25 characters. And what we have over here is the Commodore 64 PETSCII character sets. So it already comes with many different shapes. So let's say, for example, we want to make a Pacman. We can already reuse many of the shapes that comes with the Commodore 64, but we can also go in and modify this character set so we can make special characters we want to use. So let me go ahead and draw something that resembles a Pacman maze. We can use this here. Let's clean this up. Let me just change the background color to black. There we go. Better contrast, probably easier to see on the video. So I do think we need to make a couple of custom characters. So we can just select, let's say let's start from here. No, let's start from down here. Bitmap editor. Clear this out. It's our dot. We need some ends. And we need a power pill. And then I think we can add some color information. Oh, we can use this tool here. Let's color all the pills. There we go. And the power up. Oops. There we go. So I could go on and draw the rest, but I'm sure you get the idea that this is starting to look like a Pacman maze. And we could also add things like, let's say we want some scores up here and stuff. Just move this down a bit. Let's say we want something like player 1, 0. Oh. High score, I don't know, 1000. layer 2, 0. There we go. So I think you get the idea. So it's quite easy to draw a game screen like this, and you can see right away what it's going to look like. You can put your colors, you can draw everything, you can change your character sets to what you need, and we can add sprites as well. So let's say we want to add this guy here. We do need to change the colors a bit. There we go. So we now added our sprite. But you can see here it's a little bit too big. So we need to do something about that. I mean, sure, you could make it with big sprites, but you probably want the sprites to fit inside the maze here. And there's another feature of the Commodore 64 sprites I haven't mentioned yet. You can expand the sprite in X and Y. However, you can see it gets quite big, but it also gets quite chunky with the pixels being very big. But it is an option if you need it. You can expand sprites individually, and you also have the option to decide if you only want to expand X or only Y, or you want to do both of them. So it's good to know the feature is there if you need it. Anyway, let me try add another sprite. So we can try resize it so it fits inside the maze corridor. Just say edit sprite. And I think, let's just clear it out here. Like that. See how big we can make it. That looks like it fits there. Okay. So I need to draw a new ghost within this square here. Okay, I think that still works. So now our ghost fits inside the maze. Let's move the big one out of it. We can also delete it, but I'll just leave it on here. And of course we can just add more of this sprite now. So let's say we want one more ghost here. Now we can change the color. Let's make it green. So there you can see it. And if we want to have a closer look, we can hide these two here and zoom in a bit so we can see what's going on. And of course this editor here, you can also save your files, you can load your files. And a very important feature is that you can export your data. So you have a number of options here for export. But I think let's get back to that. I think I want to try draw just quickly one more screen, but do it in multicolor, just to give you an idea what it looks like. So let me just quickly create a new screen here. You can use for a multicolor test. So the first thing we notice is that the existing characters are pretty much unreadable. Because now we only have 4 pixels across and it's translated into multicolor information, just like we had with the sprites before. Let me just change the border color and the background color. I think we need to zoom this a little bit. Maybe move it over here. And let's try to draw some tiles. Let's try some colors like this. So let's say we're making some kind of dungeon crawler and now we want some wall tiles. So I'll try to draw something here. Okay, let's try to test these out. I can kind of see we get a wall pattern here. Oops. And I think we can make it look a little bit more interesting. something like this. So that's kind of what we can do with multicolor character sets. So we can build like tile sets, but I would say for tile sets and creating tile maps, there are better tools out there than the one we're looking at here. But it's just kind of an example of what you can do with multicolor character sets and what limitations you have to work with. This might look better. Anyway, just a quick example. Let's go back to our Pacman screen. Let's move this back in place. So let's imagine we have completed our Pacman screen here. Of course, normally you would want to draw some more sprites and make some sprite animations. For example, you want the ghost to look in different directions. You want the cloth moving down here and stuff like that. You don't want static sprites. It always looks very boring. Anyway, it's time to export our work. So I'm going to click export over here. And then we just say export to assembly source code. And we just copy everything in here. And then go back into CBM PRG Studio. And I already created a project. I'll just add a new assembly file. Let's call it Pacman. There we go. And then we just paste the code we got from the PETSCII Editor. There we go. Let's try run it and see what happens. And there we go. It actually sets up and draws everything on screen exactly like we did in the PETSCII Editor. So let's have a look at the code and see what it does. So the code we get here is quite nice. It comes with comments and everything, and this should be fairly self-explanatory, these places where it's been commented. And generally, because this is the video chip we're doing things with, so all the video chip or the VIC chip registers are located in $D1000. So remember the Commodore 64 memory map we looked at in the first episode. Here we can go find all the registers for the VIC chip. Just search for $D1000. And there we go. So here we have all the details of the VIC chip. So if you want more details, for example, you have registers where bits have different meanings. This is a good reference, so you should just look it up here and see what it actually means. However, once we get down in this draw screen part here, things get a little bit more complicated. And it's perhaps not completely self-explanatory. We can see they're doing some branches. These are relative branches, right? So this is kind of hard to read, but I can understand why it was added. It was to avoid having to add any labels. But relative branch -24, it can be a little bit hard to see exactly where it's jumping to. So I think let me just go ahead and add some comments on this code here, what's going on, and also we're using indirect addressing using zero-page variables. They get a little bit complicated if you're not used to this kind of code. So I'll just add some comments here. Okay, so what does it mean, these comments here? Well, it's a common technique to use address areas in the zero-page memory as a kind of an optimization. And what we're doing here is that we're storing some addresses. So in address F, B, and FC, we store the address 2800 hex, and that's the source of the screen data we're going to be copying to the screen. So that's actually where the characters of our Pacman maze are stored. And then we set $400 in FD and FE, and that is just the screen memory $400. That's also the default address of the screen memory. And then we have some color data. Remember, we did coloring of the pills and the power up, and that color data is stored in 2BE8, and we copy that to the actual color memory stored in D800. And this is our actual copy loop. So it is a little bit naughty because the screen memory and the color memory is actually only 1000 bytes, but here we're going through 4 times 256 bytes, so actually we're copying 24 bytes too much. So it's not a problem for the color memory because we do have 24 bytes extra that's not being used for anything at the end of the color memory. But at the end of the screen memory, we actually have pointers to where the sprite data is stored, so that's going to be overwritten if we do it like this. So we have to set our pointers to the sprite data after doing something like this. And I think we can find it down here with look. Right, so here we can see they set the sprite pointers after. So it's not going to cause any problems, but it's a little bit naughty way of doing it. And then this way of writing load accumulator, store accumulator, and is using indirect addressing 0 page. So this is a little bit confusing because actually what happens is that it's going to take the address stored in $FB and $FC and the data at the address stored at that address plus Y is going to be copied into the A register, and the same with the store here. So it's a little bit difficult to read it. But it does have the advantage, it's easy to increment the addresses by 256 just by increasing the value stored in these 0 page memory addresses. However, I would say for something like this, because it's only in initialization, I wouldn't go ahead and write it like this. I would actually just write it more straightforward, much more readable. Generally, I would say optimization. Don't do optimization in the beginning, just make the code work first. Because chances are you're going to be rewriting it anyway several times before you're happy with it, and then you will get to a point where you will start thinking about what you need to optimize, and then you will look at things. Okay, so for example, this, if something is being updated every single screen refresh, then you might want to optimize it, especially if it's got like inner loops like this or something. But this code here is going to run one time. You just set up your screen, and then you're not going to run it again until you need to set up another screen, maybe switch to the next level. So it's really not worth optimizing. It's much better to keep it more readable. But anyway, I think I'll save code optimizations for another episode. And we go further down here. So we have more setup, set multicolor, colorize the sprites, set the sprite colors, and the position of our 3 sprites here, including the high bit. So one thing be aware of here is that since the screen is 320 across, actually it's more than that because sprites can also move out in the border, but you have to think about 1 byte is only 256. So to move the sprite all the way across the screen, you actually need 9 bits. That's why you have this high bit. So it gets a little bit tricky when you're moving across the screen in the X-axis because you need to modify 2 bytes. And here we have the sprite expansion, X and Y, to set the expanded size, multicolor, and last it turns on the sprites, and then it just sits here and waits for a key press. So let's modify this a little bit. Let's turn it into like a main loop here at the end. So currently our screen here, let's just run it. So it's very static, there's nothing moving around, the sprites are just sitting there. So I think let's try and move one of the sprites across the screen and see what that looks like. So I'll just go into my main loop here. I'll just add 1 line. And we'll just increase the X coordinate of the first sprite. So let's try run that and see what it looks like. So yeah, that looks a little bit weird. So what's happening here is that the sprite is moving incredibly fast. So we're getting tearing because the screen is only being updated. Well, I'm running in PAL mode now, so it's only updating at 50 times per second. But the sprite is moving much quicker than that. So it's basically being torn apart while being drawn across the screen. So what we really want to do is move the sprite 1 pixel each time the screen is being updated. So let's try to do that. So the VIC chip will update the screen 1 line at a time, 1 pixel line at a time, and it will store the line it's currently updating in address D012. So what we can do here is just add a small loop here. Okay, so what I'm doing here is I'm loading the accumulator with value FB. So FB, line FB is the same as just the beginning of the lower border. And then I'm comparing it to the line currently being updated by the VIC chip. And if it's not equal, it just stays in this loop. So while it's being updating down the screen here, it just stays in this loop here. And at some point it hits, and now it's equal to value FB, and then we go down here and then we increase the X position of our sprite, and then we go one more time and do the whole thing over again. However, since this is so little we do here, we do risk hitting the same raster line multiple times in the same loop while it's still being updated. Then we could run this loop several times. We got in PAL mode, we got 63 CPU cycles for each line. Well, there are some exceptions when the VIC chip is accessing the memory, but I think I'll cover that later. Anyway, to avoid moving the sprite more than 1 pixel per screen update, I'm just going to add a small delay in here. So normally you will not need to do this, because you would be executing much more code here, but in this case we do need it. Okay, should take care of it. So this is just gonna run 256 times, and then it will bail out here, and we'll definitely be on the next raster line. So we're not gonna hit here until the next screen update. So let's try run it and see what it looks like. So now we have our sprites moving nice and smoothly across the screen, and that's kind of what we want. It's in the most 1 pixel for each screen update, so 50 pixels per second. So waiting for the screen update or a specific raster line is a very important concept on the Commodore 64. So while it's completely valid to do it like this, there's also another way of doing it. You can set up an interrupt to kick off once the raster update hits a specific line, and perhaps a little bit more elegant way of doing it. But it's still valid to do it like this. It's really up to you how you want to do it. So I don't think I will cover the interrupt in this episode here, because it's already much too long. I really want to keep these episodes very short, but I guess this was a long episode. So I recommend you download the code, play with it. There's a link in the description, and do try out the PETSCII Editor. Play with it, generate the code, and then you can look at the comments I've made here in case you want to study how this loop is working. So I think that's enough for this episode here. So if you have any questions, just leave a comment and I'll try to respond to it. So thanks for watching, and I'll see you next time. Bye bye.